Hi, everybody. So it's my pleasure to introduce the second keynote of this afternoon. My name is Graciele Posse. I work at Cadence. I work in the R&D part of routing in Novastu. And it's our great pleasure and honor to have Dr. Thomas here. Dr. Thomas is CTO and Head of Product Strategy at Zeiss Semiconductor Manufacturing Technology, SMT. He has been with Zeiss since 1998, that's amazing, holding leadership roles in design, technology, and product strategy. His expertise spans optical lithography system design and advanced semiconductor manufacturing technologies. Dr. Stammler earned his PhD in physics and conducted research at Lawrence Berkeley National Lab and IBM Almaden Research Center before he joined Zeiss. So thank you so much, and please help me welcome him.
Thank you very much for this kind introduction. So, good afternoon, everybody. I think your contribution, this group's contribution, is essential, I would say, in designing leading-edge, state-of-the-art chips. So now I'd like to invite you to join me in a kind of a journey on exploring what is necessary, what needs to be done to get these designs onto the wafer. The power of innovation. I guess I see some question marks here in the audience. The talk is supposed to be about semiconductor industry, maybe some AI, whatever, and not about race cars and rockets. Yeah. So, of course, I will talk about semiconductor and technology, but I will also come to race cars and rockets back in a minute, so stay with me. Of course, there is no talk about innovation in the field of semiconductors without mentioning Moore's Law, but of course, you know Moore's Law, the 2x doubling every 2 years, and also dealing with the cost reduction per component by that. So that is clear, and you're all very well aware of that. But I'd like to give it a little bit a different view on this, and that is the Moore's Law. When Gordon Moore, let's say, talked about this projection, kind of an way looking forward. This was kind of a description on what might be the next steps, and it was kind of started as a prediction, if you will. But it soon became much more than a prediction. It became a pacekeeper for a whole industry. And I'd like to make this point because I think it's so important to understand that Moore's Law is not just about this prediction. Yeah, it's synchronizing a whole industry. Thousands of players in the semiconductor field are synchronized in a way that they know what they need to be prepared for in the next 2, 4, 6, 8, and so on years from now. And without, any of the key ingredients, the next node will simply not happen. So the synchronization is quite essential. And there is another topic I'd like to point out, and that is this, let's say, this synchronization, this Moore's Law, is also the basis of a roadmap process. A roadmap process on a mid and long-term time scale. And this is also quite important because if you work on topics which are not be solved within a 2 years or 4 years time frame. It's good to know what the industry will need in 4, 6, 8, 10 years from now. And I will show you a few examples in the business I'm representing here, that it's good to know what's needed in 10 or 15 years from now, because some of the development times are just that long, and it's good to be prepared for what's needed then. And we all know what's the result of this, let's say, last 5 decades of Moore's Law. So when you compare in that example here, the Apollo guidance computer in the late 60s with 10K transistors in a sizable form factor, I would say. And if you compare it to nowadays, state-of-the-art AI chips hosting more than 200 billion transistors on a single chip. So that is quite an amazing progress, I would say. And I also like to, although you're of course very familiar with that, I'd like to give it a perspective in a way that this industry is really exceptional. If you would have such let's say, a roadmap, such an improvement over 5 decades, yeah, you would end up, and now I'm back with my race car, you would end up with that nice Porsche. That would be nowadays powered by 250 rocket engines, yeah, if you just would have a similar improvement in the power. You could also say, okay, well, it's about energy efficiency. The energy efficiency we drove in this industry together to a level, if you would compare this, you would be able to do a round trip from Earth to the Sun with just on 1 liter fuel. Yeah? And of course, Moore's Law is about economics. If you would just apply this to economics, you would get this nice Mercedes for a tenth of a euro cent. So, of course, I mean, that's not a fair comparison. I'm aware of that, and I will stop here. But it's just to give you an idea, as we are all, most of you, I guess, scientists, mathematicians, we are so used to 10 to the power whatever that we hardly reflect what does it mean. And this is really a very, very unique industry we are working on. Now, how did we get there? And I'd like to relate Moore's Law now a little bit to optics. And to do so, let's have a look at the so-called Abbe equation. Ernst Abbe, by the way, founder of Carl Zeiss Foundation, 180 years back. When we take this formula, you see if you want to go to smaller feature sizes, the way to go is reduce the wavelength and increase the so-called numerical aperture NA. And then there is also this K1 factor, which summarizes a lot of processes and process factors. I will come to this in a minute as well. Now, the way is clear. Reduce wavelengths, increase NA. And that's exactly what we did the last 40 plus years. And what you see here is starting from, let's say, I-line, G-line, even I-line systems, we moved our way up in NA. And when this NA reaches some limits, may it be a physical limit, may it be an economic limit, can also be that it's not economically feasible to increase the NA meaningful, then we switch to a smaller wavelength. So from I-line to KRF to 48, for example, and the same, again, moving our way up with increasing the NA. We reach the limit, change the wavelength to 193, and there we then also introduced this let's say, trick with water film between the projection lens and the wafer, making an immersion system out of it, also kind of enabled us to increase the efficient NA even beyond 1. So in that case, it was 1.35. And then a large step, of course, introducing EUV. It's more than a 10x reduction in wavelengths, which enabled quite a big jump in resolution. And just to give you a little bit of a feeling what kind of challenges we faced in this. It sounds so simple. Yeah, well, go to the next wavelength, do some NA increases. I'd like to share with you a little bit on the technical topics here when it comes to increase resolution in optical lithography. We started, but let's have a look at the full, let's say, the full refractive lens, projection lenses, like in the times with the 248 systems. Just, I would say, just a simple stack of lens elements, nicely stacked on top of each other, used the rotational symmetry. So that was basically the way to go until, I would say, the 2000s or something like this. Then we started to introduce aspherical lens elements. This allowed us to increase the NA to, I would say, beyond 0.9 regime, something like this. Then we switched to introduce mirrors in our systems, so going from refractive to so-called cutter-dioptric systems. Again, with this trick of the water film immersion system, we end up with a numerical aperture of 1.35. And the big jump, I already mentioned it, EUV, that was, I would say, quite a revolution. You might also call it a kind of a quantum leap, because things really changed significantly and completely. Yeah, so of course with EUV, 13.5 nanometers, you do not get any transmission, even not in air. So we have had to change to vacuum systems. You do not get any material, refractive material, so we had to go to all mirror systems. And in addition to that, if you compare system layout on the very left one, the nice rotational symmetric one, obviously you cannot do this with mirrors. You cannot just simply stack them on top of each other. So you have to place them somewhere in 3D, and you have to control them very precisely on their position. And in that sense, EUV was a challenge in itself, but also from a design perspective, completely different design things than when you talk about layout designs. But when you compare a refractive system, which has maybe like just a number, 30 lens elements, gives you 60 surfaces, one on the top, bottom, so 60 surfaces for the optical designer to deal with aberrations, to improve the optical performance of such a system. For EUV, however, the problem is that the mirrors have to be coated with a multi-layer stack, molybdenum, silicon, MOSI bilayer, 100 of those layers, and the reflection is done by some Bragg type of reflection, but the UV light has to go into this coating for 50 or 100 layers, and therefore a part of the UV light is absorbed. And the end of the story is that even under perfect manufacturing conditions, you end up with a transmission of 0.7 per mirror. Yeah, so 70% reflective, 30% absorption. Now, you can all do the math. If you would go like 0.7 to the power of 60, well, you could just sit there and have a nice single photon counter, and so that would definitely not work. So the optics designer, they had to improve the, let's say, the optical performance by just using only, let's say, 6, so an order of magnitude less surfaces to do all the corrections. So this is quite a challenge, was a challenge, is still a challenge, and this requirements to, let's say, do the imaging with just a few lens elements puts also huge requirements on our mirror surfaces. So the question is now, how do we get to these high precision mirror surfaces? And the answer is, we have a kind of a process chain, and we go there in loops, in iterations. Yeah? So from the left-hand side, if you look at it, we start with some rather mechanical kind of polishing, very similar to CMP in the fab. Yeah? So this is a mechanical abrasive kind of polishing procedure. Measure, polishing, measure, polishing, until we get to a situation where we change the way how we polish, and then we take the lens or the mirror and put it in vacuum, and take an ion beam source to really take off material on an atom scale level. Yeah? Also, again, in iterations. And finally, we have a final measurement, and just to give you a number, we're talking here about 20 picometers or something like this in terms of accuracy needed on the surface of such a mirror. And to measure this, you see here maybe on the right-hand side one of our metrology equipment. This is a vacuum tank, 6 meter diameter, 9 meter long, fully packed really up to the very wall with metrology equipment just to measure one single mirror. Yeah, just to give you an idea on the efforts, what is needed to manufacture these mirrors. And why is it so complicated? Because you have to polish or manufacture these mirrors to meet the specifications over 8 orders of magnitude in spatial frequencies. So just to give you an idea, if you miss the large spatial frequencies, you would just end up in getting some classical aberrations like astigmatism, coma, spherical, things you might also experience with your eyes and your glasses. So that is, I would say, classical aberrations. If you would miss some mid-spatial frequencies, your light, your EUV light, would suffer from some small angle scattering. So the light will be scattered, but the angles are still small, and the projection lens is capable of, let's say, getting all this light and image it on the wafer, but not at the right spot, so you get flare, reducing contrast. You don't want to have that. If you miss the high spatial frequencies, so the high spatial frequencies give you a large angle scattering, this will be blocked by the aperture of the lens, so it will not end up at the wafer, but it will not end up at the wafer, so it will reduce throughput and therefore productivity of your tool, and you don't want to do this with precious EUV photons as well. So that is the big challenge when it comes to providing optics for EUV lithography. And as a hobby astrophotographer, I could not resist to put in this slide here. This is I would say, a quite beautiful image from the James Webb Telescope of the edge of the Carina Nebula. This image got famous as it was one of the first published photos from images from James Webb Telescope. And why did I put it in here? If you compare the requirements for our EUV systems to state-of-the-art other kind of optical instruments, telescopes, earthbound or in space, you see that our EUV mirrors are, I would say, 2 orders of magnitude more demanding than any of those other optics. And keep in mind, we are not building one of this mirror every 5 or 10 years. We build dozens of them every week and month. So to have this in a kind of a full production way, that is a big challenge, and that is a little bit also why I always, sometimes, quite often actually, I got the question, so now that EUV is so, it's clear, it's in full production, and it's so a critical technology. So where's competition, and why are not all the other players are also offering EUV tools? I hope I could show you a little bit that it's not that easy just to step in and build these kind of tools. Yeah, so I talked a lot about the optics. Optics in a way, again, I'd like to put it always in comparison. So if you would polish the city of Bonn to the same accuracy over the whole city of Bonn, we would face only 200 nanometers of deviation from the target figure. Yeah? But I also want to point out, as I mentioned, these mirrors, they have to be held in 3D at some position with a very accurate pointing. Yeah. And also here, I could have another talk for an hour on the mechatronical part, but just to give you a number, the pointing stability of these mirrors are also, I would say, in an insane regime. So we are talking about tens of picorad tilt accuracy. So again, if you would translate this, you would be able to steer a laser so precise that you would hit a golf ball on the moon from the Earth, so 400,000 kilometers apart. So to get all this done, a lot of things to be taken care of. And the question is now, why are we dealing with such complexity? Why is the industry willing to spend millions for such tools? And isn't there anything else which does the job much more, I would say, cheaper or whatever? So I'd like to give it also a little bit a change of perspective now. And that is, let's consider optical lithography as a part of information transfer. Yeah? What we do is the source of, so first of all, you find yourself on the very left-hand side. So we have a target design, and then we need to, given the situation that our transfer system, the optical lens, has a finite bandwidth, so we first need to add some sub-resolution features, do some OPC, and then write a mask. And then this mask, which contains a little bit more information than the original design, this mask will then be transferred onto the wafer, will be processed, and in the end, I would say you end up with the desired design pattern. Fine. Now, to get to some numbers, for this group, I do not need to introduce these kind of things, just to, of course, we do some pixelation, and then there is some bits per pixel, depending on the signal-to-noise ratio, but based on with very I would say, textbook level kind of considerations, we end up with a graph like here. And this is also kind of a little bit of a historical view, data from ITRS of 2008, 12, and 15. But it nicely illustrates one thing, and that is if you look at the solid, the circles and the triangles, you see that is the mask data content. Yeah? And the solid line is the data which is transferred, which is on the wafer at the end. And what you see is that on one hand, the mask contains, as I already described, more information than it's printed. That's a finite transfer function for the bandwidth for the optical system. But you also see that when it comes to these red triangles, at some point one thought, okay, well, when we introduce EUV, then it's maybe not necessary to do all this OPC stuff and all these assist features because you have enough room. And that's why you see it was thought that it's kind of equivalent. So what is on the mask, you get on the wafer. But moving forward, I think it's clear that even for EUV, we benefit a lot by doing this kind of OPC and additional measures to improve resolution. Now, the question is, if we consider the projection lens or the optical lithography system as a data transfer system, what are the knobs to increase this data transfer? And first of all, when you look at the bandwidth knobs to improve or increase the bandwidth, we already talked about this smaller NA, smaller wavelengths, larger NA. These are ways to improve the bandwidth of the projection lens. And you see with the current state-of-the-art projection system, the so-called high-NA EUV, we get to roughly a little bit more than 25 gigapixels per square millimeter in data bandwidth. And talking maybe a few words about high-NA. So already 2 years back, Intel was the first of the big players to introduce high-NA EUV. Since then, I think all of the major players, all the major fabs, they have their high-NA tool installed and working there in R&D, not yet HVM. We see the quality of the imaging, like here on this plot, together with IMEC at the tool at ASML. There is superior imaging quality of high-NA, and not only about pattern fidelity of, let's say, contact holes or lines and spaces, but also if you look at, let's say, 2D interconnect patterns, where you can do just a single exposure for the 2D pattern, where with low NA you would need 2 or even 3 mask sets, 3 layers, if you do this in multi-patterning. So this is quite encouraging. But there is a but when it comes to what needs to be solved, and that is high-NA exposes only a half field, not the full field, only a half field. And why is that? I already mentioned these EUV mirrors. They have to be coated with molybdenum silicon bilayers. And of course also the mask is a mirror, yeah, if you will, based on the same kind of multi-layer system like the mirrors in the projection system. Now, if you want to kind of separate the incoming angle from the outcoming angle on the mask, so the reflective light, you have to kind of separate this, these two beams. You have to be careful that you must not increase the angle between incoming beam and reflected beam at the mask to a large extent, because then your reflectivity will immediately drop significantly. So it's important to keep these angles at the mask very small. But if you go to high NA systems, if you increase the numerical aperture by physics, you need to increase the angle of these individual light cones. So in order to not let them overlap, you would need to increase the angle at the mask. And the trick to avoid this is to do this this change in the light cone angular distribution, which is determined by the magnification. Yeah, you change this only in one direction where it's needed, and keep it in the other where it's not critical. And that's why we ended up in, so the typical systems have a 4x demagnification, and for the non-critical direction we keep the 4x demagnification, and for the here in that sense critical direction we increase the magnification to 8, ending up only in the in half-size field. So, if you want to do a nice patterning here on a full field, you need to stitch. And so, from a scanner point of view, we can support this stitching. There is a little bit of extra, I would say, space available for the stitching, but you have to take care of where to put your stitching line. And there are, of course, many ways to do this. I brought here 3 different ways with me. That is, on one hand, you can do just draw your stitching line around the IP blocks. Yeah, so to avoid to cross any IP block, just move your way around them. The second one is, you can, if you find a way through your IP block in areas which are not that critical, that might also be a solution. And of course, you can always reserve some space within the IP block to allow for stitching in that area with some impact of your real estate, of course. So just want to point out, we can deal with stitching, so building larger die sizes out of even the half fields with high NA, but you need to consider this even in the design phase to make sure that we find I would say a nice stitching path around the IP blocks or through the IP blocks without harming the performance, of course. Now, a second knob to deal with the increase of bandwidth and data rate is this K1 factor. The K1 factor is, I mean, when you look at the graph on the left-hand side, there is, again, this blue curve, which is the theoretical maximum of a bandwidth of such a projection system, which is given at a K1 of 0.25. But process parameters are typically leading you to larger K1s, and so therefore lower resolutions. And what you see is in red here, also the evolution of this K1 parameter, if you will. So in the beginning, you see there's quite a large gap between theoretical limit of an optical system and what was used in practice. Over time, processes matured, more fancy illumination settings were established, and K1, as I would say, approached the theoretical limit of 0.25. And when you look at around the 10th year, so you see that immersion almost reached this 0.25 value, because at that time we were kind of late in introducing EUV. So there was a huge need for the industry to, let's say, push immersion to the limits, yeah? And that is why you see K1 factors of almost the theoretical limit, I would say, meaning that you have very well controlled and optimized processes. So with EUV, that gap will widen again, but as EUV processes mature, I'm pretty sure they will end up close to the optical bandwidth theory value. Okay, I need to. I guess most of you know what's behind OPC, so you of course look at some of your critical areas on the chip, and if you would just print them with some standard settings, you would end up in maybe non-yielding or bad yielding processes. So what you do is you do a co-optimization, introducing features, additional features on the mask, and also co-optimize your source. So the light distribution, angular light distribution of your illumination, and then you end up with just the right illumination setting and features, additional features on the mask. So that is what you might know very well. Here is just also like a little bit of an historical overview on how we introduced more flexibility, more capabilities into this illumination system to deal with these source mask optimizations. So we started with, of course, we call it conventional settings or annular settings, and then we added dipoles, quadrupoles to the family, and then at some point the so-called pupil fill ratio, that is the fraction of the area of the pupil which is illuminated by light, and the smaller this is, the more you concentrate the light in spots where you'd like the light to be, the more flexibility this gives you, and typically you can improve resolution with that. And then at the end you see here, just behind me, I would say some almost arbitrary patterns which are possible nowadays for illuminating the reticle. And we are not stopping there, just to give you an idea. So for EUV, we are currently working on the next generation of illuminator, which can decrease this pupil fill ratio by a factor of 2, giving even more flexibility for source mask optimization. As I said, as EUV processes mature, and we are entering low K1 imaging there as well. Maybe only one short remark. Of course, Noise is also a big topic. There is noise on the receiving side, which yields to defects in the process. And then there is also a noise like shot noise, where you have with a larger photon energy with EUV, you get more stochastics, if you go to lower doses. And then you see there is a nice dependency on this shot noise with dose, quadratical dependency. So you could just add more dose and get less shot noise, but again, more dose is less throughput. So we have to find a sweet spot to get the right patterning and do not sacrifice throughput of the tool. And with that, I come to the part where it's not just about bandwidth, but it's real data rate. There's the time contribution to it, so to speak, with throughput, the knob throughput. And if you look at the graph now, you see there is this orange dotted line and an orange solid line. And the dotted line is basically the data rate we achieved at the point of introduction of the tool, and later with the solid line, which is kind of factor 2 to 3 higher than the dashed one. That is by using improvements in throughput, like faster stages, higher transmission of the optics, and so on. And now back to the question where we started: why all this hassle with optics? And if you want to compare it to an alternative way to print your features, I just picked for comparison a mask e-beam writing tool, multi-beam tool, state-of-the-art tool, by the way. It offers you like 675 gigabits per second as a data rate, whereas the optical lithography is at least 2 orders of magnitude faster. So that means writing a mask within hours, printing that mask on the wafer within seconds. And that is why I think optical lithography is, I would say, very key if you look into high volume manufacturing of semiconductors. There is no, I would say, alternative technology which can compete on the throughput requirements, on the, let's say, on this information transfer from a design physically made into the mask, then onto the wafer. And of course, we're working on the throughput improvements as well. Just one slide here. Together with ASML, we're working on a high productivity platform for EUV that will also increase the throughput of EUV systems by another almost factor of 2, adding to this bandwidth. Then before I wrap up, of course, I'd like to mention that with all the current situation in AI and the demand AI is showing and driving the industry, there is, of course, a lot of different technologies necessary. So, of course, there is not just this monolithic part where you go for shrink according to Moore's law. You have to also look into this 3D integration schemes, chiplet integration, advanced packaging, and I think more sooner than later you will see also this let's say this integration of photonics, co-packaged optics, bring the photonic communication closer to the chip system, or even connect your chip packages via photonics. So this is kind of a, I would say, current view on the situation. I brought this up because I think it's not either this or this technology. It will be for sure an end story. So we will need, I think, all of these things. We will need shrink to get the chips more energy efficient. Yeah, I mean, you might argue for a server farm if you have cheap small nuclear plants, so it's not a big thing, but you don't want to carry a nuclear plant with your smartphone, and if you go to the edge with AI applications, I think it's becoming critical to also work on energy efficiency on chip level, and therefore I think shrink will be an important component. Also, Moore's law is kind of slowing down. I like to bring the message across. I think it's far from being dead. It's discussed this, I think, for 10 or 20 years regularly. It will change. It will be a combination of different, I would say, technologies going hand in hand, but there will be a shrink roadmap as well, and we are also preparing with the next generation. So we are working on design concepts for, we call it Hyper-NA tool, which then would also, with these dotted lines here, increase your data rate transfer rate by another factor of 2. Yeah, and with that, I would say optical lithography is the way of really doing high bandwidth information transfer from your design onto the wafer. There is less, I would say, little alternatives. Optical lithography has driven Moore's law, I would say, for the last 5 decades, and most likely will drive it for the next decades as well. And as I pictured here, I think Gordon Moore and Ernst Abbe, they would be delighted to see that these two things are going quite well hand in hand. And with that, I'd like to end my talk, and thanks.
Yeah, thank you so much, Thomas. We have time for one question.
So it was to me a surprise how much energy is lost in bouncing back from a lens. So does that mean that these lenses need to be cooled because in vacuum they have not much way to go? Or can you share a little bit about that?
Yeah, you're on the spot here. Yes, so with the demand on increasing throughput of these systems, we increased, of course, the source power, talking about 1 kilowatt source, 1 kilowatt EUV, and then there's also out-of-band contribution to that. So that is definitely heating up the mirrors, and we do have quite some, I would say, different means of dealing with the heat, adjusting for it. Cooling is one way. There are other means to deal with the heat, but it's a very critical and very demanding topic for high productivity tools. Yes.
Jürgen Scheible from Reutlingen University. We microelectronic guys are used to talk about nanometers, and you talk about picometers. This is really impressive and very amazing. My question is there any other company, or let me better say, any other player in the world who can do what you are doing?
So today, the short answer is, I would say no. Yeah, in a way, Are there others working on that? For sure, definitely. Then you have to distinguish, I would say, between companies and countries, if you will. For a company, you have to keep in mind that the investment, so we developed this EUV technology for now 25 plus years. This is a tremendous investment in also money-wise, and of course in resources, engineers, a network, suppliers and partners, and this, I would say, it's the boundary to step into this field is quite high. So I would assume that it's very hard for a startup or something like this to enter this field. It's maybe different, of course, if you have, I would say, backed from a government money and focus, then of course there is work going on here. Yeah.
Yeah, I think we have a panel now, but very interesting talk.
I will be around, so yeah, in the next.
Yeah, I'm
break
pretty
or so,
sure
yeah.
we have more questions. Thank you so much for the very interesting talk. Thank you, hearing.
Yeah, thank you.